Okay, topic 4.5, standing waves. There are no formulas, but you need to draw all of the wave patterns I draw. IBO expects you to be able to derive the equations based on your ability to draw the standing waves. All right, so let's just look at the nature of standing waves. We have two waves that are traveling in this GIF, a wave moving to the left in blue and a wave moving to the right in green. If you're colorblind, I'm sorry. So what you see is with this red wave, the red wave is the resultant wave. It's the sum of the two waves, the blue and the green's displacements. What you'll notice is that unlike the two traveling waves, the red wave isn't moving laterally, it's only growing and shrinking. Its lobes are oscillating up and down. This is a standing wave. So again, traveling waves moving left to right, the standing wave just oscillating up and down. The standing wave has two important properties. First, it does not travel left or right as the blue and the green wave do. As we've seen before, its lobes only grow and shrink. Any point where the standing wave has no displacement is called a node. There's a node right there. Any place where the standing wave is crossing the x-axis that has zero amplitude, that's a node. The lobes that grow and shrink are antinodes. So antinodes are places with maximum displacement or maximum amplitude. All right, you may be wondering, how could a situation develop in which an identical wave comes from the opposite direction? Well, wonder no more. If you've ever plucked a stringed instrument, a wave travels from the string in the middle to the ends and gets reflected at a boundary. That's the condition needed for a standing wave, a change in boundary that causes the wave to reflect upon itself. So imagine I pluck a string, and there you have it, a standing wave is formed that oscillates. Note that for this, there are two nodes and one antinode. All right, so observe that precisely half of a wavelength, half lambda, fits along the length of the string, so we can make an equation. Lambda over 2 equals L. You can see I have two nodes, one antinode. That's half the condition of a wave. Thus, lambda equals 2 times L. And since the speed of a wave is frequency times lambda, we see that the frequency equals v divided by 2L for a string. This is the lowest frequency possible from the string configuration, so it is the fundamental frequency, or F1. The fundamental frequency of any system is also called the first harmonic. So the next higher frequency for a plucked string has two antinodes and three nodes. We now see that lambda equals a full L. And since again the wave speed equals lambda times frequency, frequency of the second harmonic is v over L. We can also set up standing waves in pipes without strings. In the case of pipes, longitudinal waves are created instead of transverse waves, and these waves are reflected from the ends of the pipe. These are just sound waves. So consider a closed pipe of length L, which gets its wave energy from a mouthpiece on the left side. So this is the mouthpiece open and someone is blowing into it. The wave travels down the length of the tube, hits the end, and gets reflected. In this case, the length of the tube encloses 1/4 of the wavelength. So the fundamental frequency, or the first harmonic, is the wave speed divided by 4 times L. And this is now the appearance of the second harmonic. You should sketch all of these. In this case, this is 3/4 of a wavelength fits inside of the length L of pipe. So the frequency of the second harmonic is 3 times the wave speed over 4L. And then this is a sketch of the third harmonic frequency. In this case, we get 5/4 times the wavelength equals the length of the pipe. So the third frequency is 5e over 4L. So why must the mouthpiece end always be an antinode? Because this is the source of the wave. It has the highest energy, the highest amplitude. And why must the closed end be a node? Because the air can't move there. It must reflect at this boundary. In the open-ended pipe, you can have an antinode at the open, and because the medium can vibrate there, and of course, another antinode at the mouthpiece. So here we go. This is the first harmonic frequency for the open-ended pipe. Each end of the pipe is open to the air. So in this case, you have half of a wavelength inside that fits inside the length of the pipe. The harmonic frequency is V over 2L for the open pipe. This is the second harmonic frequency. In this case, you have a full wavelength fitting inside. So the fundamental frequency is V over L, or the second harmonic frequency is V over L. And then we have the third harmonic frequency. 3/2 of a wavelength fits inside the pipe. So the third harmonic frequency is 3V over 2L. The IBO requires you to be able to make sketches of string and pipe harmonics, both open and closed, and find wavelengths and frequencies based on the length of the pipe. Finally, we have a comparison of standing and traveling waves. This is the summation. The energy of a standing wave is not transferred, but the wave has it stored in each antinode. The energy of a traveling wave is transferred from source to receiver at the wave speed. The standing wave has maximum amplitude different for all points in the medium between nodes, but all points of the medium in a traveling wave will eventually achieve maximum amplitude. So all particles in a standing wave vibrate at the same frequency, and these vibrations are simple harmonic oscillations. Same for the traveling wave. The wavelength of the standing wave is the same as the component waves, and for the traveling wave, it's the distance between the crests. The phase for each point in a lobe of a standing wave is the same, but adjacent lobes are phase shifted by 180. That should make sense. One's oscillating up as the other is going down, and the phase for each point along a single wavelength is different for a traveling wave. The standing wave pattern doesn't move, and finally the traveling wave pattern does move.